Hello, I'm John Edwards and I'm going to tell you a little bit about damp, mould and condensation as part of Damp and Mould Action and Awareness Week. I can tell you a little bit about myself first so you know why I'm here today talking about this subject. I have a trade background, but in 1981 I got a job as a trainee building surveyor, and for nearly 5 years I didn't do much else than investigate damp, mould and condensation amongst all other types of building defects. And whilst at the time I wasn't too enamoured with doing that every day, when I look back, I think it was probably the most perfect foundation that anybody could have in dealing with lots of things to do with existing buildings. Today we would call that building pathology, but in those days it was about building defects. So let me start by telling you a little bit about what I'm doing today. Today I'm a director of a small consultancy practice, and we deal a lot of damp, mould and condensation in all different types of buildings, from social housing to, at the moment, a grade 1 landmark listed building in the centre of London to a Cold War nuclear bunker. So we deal with lots of different issues concerning damp, mould and condensation, but other issues as well, such as refurbishment, conservation and almost anything you can think of to do with existing buildings. So let's make a start. So this is what we're going to be looking at in the next hour, understanding damp, mould and condensation as much as we can do so in that very limited time period. So what is the problem? What's the problem with damp, mould and condensation? Well, let's look at a list of these questions. And these are the questions we're going to try and answer in the next hour. And then at the end, we'll come back and see how well we've answered them. So first of all, what are the most common causes of damp and mould in homes? How can landlords and housing providers identify issues before they escalate? What are the short and long-term risks to residents if problems are ignored? And which interventions are most effective in tackling damp and mould at source? And how can contractors and surveyors work more effectively with landlords to reduce reoccurrence? We know it's a problem. It's in the news all the time. You don't have to look very far, perhaps every week, to find a new story about problems with damp, mould and condensation in buildings. I believe it's almost at an epidemic rate. But you know what? It hasn't always been this way. Some people say to me, when did I see it get worse? Well, it's always been around. It was around in the 1980s, but during the 1980s, I saw when it got worse. It was when we took out the old windows, old timber and metal windows, and replaced them with plastic windows with draft proofing. And we removed the fireplaces and we installed a couple of fans. And that is when I saw the situation get worse. And it's very, very bad today in many circumstances. This has raised the profile. This very sad death of this infant child has really raised the profile of this epidemic problem. This person's not the only person to have died from mould issues, but it's the one that's really going to change things. It's bringing about a law that we call Arab's Law. And within Arab's Law, we have very, very strict timescales to comply with. Or I should say, social landlords have got very strict timescales to comply with. And there are some implications for that. And first of all, let's look at what these timescales are. So an investigation must commence within 10 days of the reported or known damp issues. A written summary of the investigation findings shall be reported to the tenant now. It's almost as if the tenant now is the client, reported to the tenant within 3 working days of the conclusion of the investigation. The summary must include the name and job title of who investigated the problem, so that person will most definitely be in the spotlight. Also including the details of any hazard identified, the next steps included, an anticipated timeline for repair and a schedule of works to be developed. Relevant safety work must commence within 5 working days of the investigation conclusion, and steps to undertake the further work which is necessary to prevent hazards reoccurring should begin within 5 working days of the investigation conclusion. But if this is not achieved, this must be done as soon as possible and physically commence within 12 weeks. If the hazard is judged as an emergency, work must commence within 24 hours. and any work is required to be completed within a reasonable time period. And the last point is very important, I think. It's important to maintain accurate records so you can perhaps defend yourselves in the future, if you are a social housing landlord, that you've done what you can within the specified timescales. So my conclusion from this, some people may have a different take on it, but the maximum timescale for initial work to commence is 15 working days from the hazard being reported. This does not have to be all the work necessary in order to prevent the hazard reoccurring, but this work must begin within 12 weeks. Now, for many organisations, that is a very tight timescale. In fact, you could say that all of these timescales are pretty tight. In having to include the name and job title of who investigated the problem, I would say places great responsibility on the individual who has undertaken the analysis. It might suggest that should a dispute arise, that their credibility and expertise will be under the spotlight. And I would also say a qualification in the subject could assist in evidencing their credibility, and that's something I will talk about towards the end of this presentation. Note that the initial reporting by the tenant could involve comments made verbally to anyone within the landlord's organisation, for example, maybe somebody servicing the gas boiler. But what is damp, mould and condensation? And let's try and break it down into finding out, what is it? Well, number one, you could say it's moisture levels above the thresholds for each material type causing damage. So all materials in a building will have a different threshold at which moisture is a problem in terms of deterioration of that material or a lack of performance. And that's something we'll come back to in a moment. Number two, it could be penetrating through walls. 3, rising through walls and floors. 4, leaks through roofs. 5, leaks from pipes, drainage, and anything that contains liquids that leaks. And 6, low surface temperatures leads to high levels of relative humidity. And if the relative humidity is 100%, then we're going to get condensation. But even if it's at a lower level, then it could also be a problem in terms of mould. That brings us on to number 7. Persistently high levels of relative humidity on surfaces increases the risk of mould. And 8, low heat, low temperatures inside buildings increases risks of low surface temperatures. And 9, a lack of ventilation generally in a dwelling increases the persistency of high levels of relative humidity. So going back to that number 1 item in the last slide, and I mentioned that different materials can cope with moisture in different ways. So if we look at this table that is based upon a BRE document of a few years ago, we can read the column titled Materials, and then we can read the column titled Investigate the Cause. And that indicates for timber that if you determine that timber has an 18% moisture content, then that's too much, because that's the threshold at which moisture could be a problem. But if you look down that list of materials, you find we got much lower threshold moisture percentages at which moisture is a potential problem. And if we go right down to the bottom, we see plaster is nowhere near 18%, it's 2%. 2%. Now we can only use this for guidance, only for guidance. But when it comes to determining the amount of moisture present, then we need to use the right tools and equipment, which I'll come on to in a moment. But for timber, we're going to use that 2-pin moisture resistance meter. But we're not going to use that equipment on any of these other materials because it will normally exaggerate the amount of moisture present. So for plaster, for example, we'd have to use a carbide test, which means extracting the material from the actual plaster itself and analysing it. But that way we can see the true moisture content. And if we use the wrong tools, and we are using tools which will exaggerate the moisture content, then we may be investigating a problem that doesn't really exist. So we need to be mindful of this type of data when we are investigating moisture in buildings. So I mentioned the tools. These are the tools we should be using and a lot more. The most important tool is you, the investigator, the surveyor, how much you know, what your expertise is, what you can see, what you can hear, what you can smell, tap, thump, stamp, what does it sound like? All of those things, plus using equipment. The most important piece of equipment, I would say, is the hygrometer. And that particular model there is combined with a capacitance meter and a moisture resistance meter for timber. I don't suppose we'll have too much time to talk about the nitty-gritty of those particular tools and what they are. But the second most important piece of equipment is the thermal imaging camera. I've been using a thermal imaging camera for over 10 years, and you know what, I don't even understand how I managed to do my job properly before I used one. It is so useful. But all these other tools and equipment are also useful for us, maybe not all of the time, but a lot of the time. But one piece of equipment that will be useful to you all of the time is the vane anemometer with a hood to test the fans. Now I'll give you an example of how important this is. A good few months ago, I was investigating, to cut a very long story short, myself and my colleague, we were doing a reconnaissance survey of many homes. It was supposed to be 100, but we couldn't fit it all in terms of our capacity. So what we did an external inspection of the homes externally. This is social housing. And then we went inside 12 properties in a day. 12 properties that we knew had moisture problems because the client had told us. And so when we go into a property, we have our thermal imaging camera, we have our hygrometer, we have our capacitance meter, we have our 2-pin moisture resistance meter, and we have our vane anemometer. And when we go in, the first thing we do is speak to the occupants. And we may say, we notice your trickle vents are closed. And the answer will be, well, yes, obviously, we don't want to lose all the warmth we're creating from putting the heating on when we can afford to, out into outer space. Night latches, same story. Then we ask, do your fans work? And the typical answer is, well, we don't know because we don't turn them on. Okay, you don't turn them on. We turned them all on. 12 dwellings, therefore 24 fans, and they all worked. They all worked. But when we tested those fans with the vane anemometer, guess how many worked properly? 1. So who's at fault here? And this is where it becomes complex when we're trying to apportion responsibilities for mould problems, and all these properties had mould, all of them without exception, to varying degrees. So who's at fault? Is it the occupier because they're not turning the trickle vents on or turning the fans on? Well, even if they were putting the fans on, most of them didn't work properly. So again, it's not just their fault, is it? So what I'm trying to explain is that this is a complex issue when we're trying to apportion responsibility. And that's what we've got to do with Arab's law and other laws. So we've got to be able to actually analyse things properly. And you can only do that when you are using the most correct and appropriate equipment. And also follow a process. So this is my process for damp, mould and condensation investigations. The stages from 1 to 10 are detailed in those green boxes. And if you look at the boxes, the black boxes, most of them leading into those green boxes, you'll have a good idea what this entails. This is what I teach in my course on damp, mould and condensation for the Environment Studies Centre, which achieves a Level 3 award qualification in damp, mould and condensation. And what I want to do is briefly take you through these stages so you can see what's involved in undertaking a proper investigation. And in undertaking that proper investigation, starting with your investigation before you ever go to the building, when you're doing all these things, you're taking information, you're making your observations, you're thinking, you're joining up the dots, you are investigating at every single stage until you get to stage 10, where you're going to be doing your final analysis and reporting. So the first thing we do is that desktop inspection. And you can see what it involves: understanding laws, understanding different types of moisture, understanding building types of different ages and their relationship with moisture, understanding what is really damp, mould and condensation, different types and aspects of mould, understanding the causes of moisture problems, And of course, most importantly of all, you need specific information about your particular building that you are investigating. And not just the building itself, its setting, its environment, the geography around it, and its location generally. And that requires an excellent understanding of the subject matter. And once we've done all that, and bear in mind, the better the pre-inspection is, the better the desktop inspection is, the more effective we will be when we get to the building itself, and the more economic we will be with our time. So we start our site inspection at stage 2. And the first thing we do is have a discussion with the occupant. We want to find out their side of the story. During the desktop inspection, we may have ascertained that this has been done, that's been done, or this has been resolved and that's been resolved. What is their side of the story? What do they know about these issues? Will their story be different to the official one you researched into files? And also find out from them the way they are occupying the building. And also, if they know of anything that they think is important enough to say, look, I think this needs to be resolved now. We're talking about urgency now. And if anything urgent is to be undertaken, then you can deal with that straight away. So when it comes to looking at the way occupants are occupying buildings, we're looking at moisture generating activities. And the greater the number of moisture generating activities being undertaken, the greater the moisture being produced will be. And what we're looking for really is moisture generation that is above the norm. We're looking at the number of people, we're looking at what they're doing, but we're also looking at other things as well. If you've got water leaking through a roof, that's going to increase the amount of moisture in the building. So we've got to understand that. What we must also be doing is working to authoritative standards, authoritative documents. And the most authoritative standard in the UK for dealing with moisture in buildings is BS 5250/2021. That's the one I use. That's what the course I've told you about is largely based upon. In that particular document, it indicates that you need certain information from the occupants of buildings. And it says, words to this effect, you need to write down the questions of what you're going to ask the occupants when you arrive in a building, and you've got to note those answers. And if you then work to information that's contained in BS 5250, you can actually calculate the amount of moisture that's being generated. It will not be accurate, will it? You're relying upon what you're being told, but you'll have some idea of the amount of moisture being produced, and then you can compare it with the other dwellings you're going into, and how does the quantity of moisture being produced compared to other dwellings also relate to the condition you're finding your building in, your dwelling in. So that is a very important part of the analysis. Of course, we're looking for overcrowding, aren't we really? Overcrowding is creating too much moisture. And one of the problems we have with ventilation when we create buildings, when we construct buildings, is we take a one size that fits all to ventilation. And that is not the approach we should be taking. And calculating this information can help us work out what ventilation we really do need in a dwelling. And once we've done that, then we'll start with our external inspection. And that external inspection isn't just the building itself, but it's also the location around the building, the geography around the building, and also taking data. Using the hygrometer, taking data such as temperature, relative humidity, absolute humidity, and so on and so forth. And once we've done our external inspection, we'll start internally. And internally, we'll be making our observations, including the changes which are taking place. And again, we collecting data, and normally would start at the top of the building. And then within each space, we undertake the activities which are explained in stages 5, 6, 7, 8, and 9. So when we go into each interior, that's what we'll be doing. So we'll be making our observations about dust, debris accumulation. That's important because dust and debris provides great food for mould to grow. We'll be looking for clutter. Clutter is important to understand because it may restrict the circulation of air around the building, and you could get stagnant air then maybe at the back of furniture, which is placed against the in the enveloping walls of the building, or obscuring heat emitters. So we need to do that in each particular space we go into. And also in each particular space we go into, we must do a visual inspection for damp, mould and condensation, and we can relate to what we're seeing in terms of mould to a library of different mould types to get to understand as best anybody can what mould we are actually seeing in front of us. That will not always be accurate, but we're going to have a go at doing it. That's what we should be doing. And we'll also be making our observations about the condition of timber and damage to other materials contained within the building fabric. And once we've done stage 6, we'll be on stage 7. That's when we'll start using the hygrometer and the thermal imaging camera. That's very important. That is very important indeed. In fact, the ideal range for relative humidity inside a dwelling is between 40 and 60%. That is for human health. And if you look at the chart on the left-hand side, if relative humidities are too high or too low, they will give rise to problems such as bacteria, viruses, mould, fungi, mites, asthma, and so on and so forth. But you will note from this, what we are chiefly talking about here are problems that affects the health of the people occupying the building. So if you go into a building and you're not going to use your hygrometer, it could be a dwelling where the occupiers are so house proud they don't want anybody to see any defectiveness in their dwelling. So they may be almost continually redecorating and patching up so it looks good. And if you go in without your hygrometer and without the necessary equipment, you may think everything looks fine. And you probably don't understand that the occupier might be going back and forth to the doctors because she isn't very well. And she may not be very well because of the environmental conditions of the home in which she is living. If you use the hygrometer, you will know whether relative humidity levels are too high or too low, and usually they're going to be too high if they are outside the norm. And then you will realize what the implications are for the occupants of that building. And that's why we need to do it, because we need the full story. And just imagine, if you are doing this exercise as part of a retrofit assessment, then if you don't go into the property with the right equipment and understanding, for example, the relative humidity levels, and you go in and you think it's fine, the retrofit project progresses, it's implemented, it's finalized, it's completed, and then we do the post-occupancy evaluation. Okay, and if we do a proper one, and if people complain enough, there will be a proper one, then somebody will go in, doing a post-occupancy evaluation, they'll be using the hygrometer, and they'll be relating to the complaints made by the occupant that this retrofit is making me ill. And if the post-occupancy evaluation indicates that, oh yes, the relative humidity levels are too high, if they can't compare it with data taken at this particular stage, they don't know whether the retrofit project is the reason why the situation's worse, or it was not too good in the first place, or hasn't made any difference. You've not got a full picture. So it's very important, anybody doing any investigation of a building for whatever reason, to take this data and use the right equipment. So what is condensation? I've already briefly mentioned it. The condensation is when we got too much moisture in the air. Condensation is when we have 100% relative humidity. We know that as dew point. That is the saturation point, when the moisture cannot contain any more moisture without it condensing, without condensation occurring. That's what condensation is. But what about condensation on the inside face of glazing and other cold surfaces? Well, I've already mentioned that the highest level of relative humidity inside a dwelling, inside a space, should be 60%. But if that air with moisture within it then meets up with a surface such as the inside face of a single pane of glass, where the surface temperature is at or below the dew point, then the air will go from 60% to 100% instantly. And that's when we get condensation on that glazing, when the air is cooled on meeting that cool surface to the extent that condensation occurs, because the surface temperature is at or below dew point. But condensation is not the only problem. High levels of relative humidity, even if they don't reach 100%, is a problem. High levels of relative humidity, not at 100%, but high levels can give rise to bacteria, viruses, mould, fungi, mites, and so on and so forth. And that can lead to ailments such as runny nose, congestion, eye irritation, sneezing, coughing, a sore throat, skin rash, headache, lung irritation, wheezing, and so on and so forth. Let's look at this chart. Condensation is not the only problem. If we look at row 1, that's the saturation point. 100% relative humidity, we have got condensation. But you don't need condensation for, say, mould to grow, because if you look at row 3, if we got 90% relative humidity, that is enough for mould to start germinating. And then if we never see 90% ever again, but we see 70% most of the time, as we can see in row 6, that is enough for mould to start colonizing, and it will colonize and it will sustain itself if we have 70% relative humidity most of the time. So what can we do to remove this persistency? Think about it. What can we do to remove this persistency of high levels of relative humidity? Think about it. It's something we've mentioned already. Yes, it's the V word, ventilation. Yes, ventilation will reduce the persistency of high levels of relative humidity on surfaces. So that's what we need. We need to make sure we've got decent ventilation. In this example here, I'm highlighting that we have the hygrometer is picking up the fact that we have 100% relative humidity. We've reached dew point. We've reached saturation point. We have got condensation. And the temperature at which we've got that dew point is 12 degrees Celsius, and therefore the dew point temperature is 12 degrees Celsius. The warmer the air, the more moisture can be held within it. So if we increase the temperature, we will reduce the relative humidity level. The question is, what temperature do we need to reduce the relative humidity level down to a safe level, which would be 60%? The psychrometric chart, which you can see in front of you, will enable you to calculate that. And it's calculating that if we increase the temperature to 20 degrees Celsius, the relative humidity will go down to 60%. But it's got to stay at 20 degrees Celsius. And if it doesn't, if it goes down to, say, 15 degrees Celsius, then the relative humidity is going to go up to 83%. And if it keeps on going down, if the temperature keeps on going down to the dew point temperature, 12 degrees Celsius, then again, we've got condensation. Now, the psychrometric chart is so important for us to understand these issues because it helps us understand how all these things relate to each other. So on the bottom horizontal line, we have temperature. On the top horizontal line, we have the relative humidity. On the curved line, we have the dew point temperature. On the vertical line, on the right-hand side, we have a representation of absolute humidity. Working out how different temperatures affect the relative humidity. So the hygrometer is going to give us the data to start this process off. The hygrometer allows us to place information on this chart. Temperature at 12 degrees Celsius, relative humidity at 100%, so we got condensation, a dew point temperature at 12 degrees Celsius. That's what we've got. And so if we want to bring that relative humidity down to 60%, you can see we mark 60%, and if you follow that curved line down, starting at where we got that red cross of 60%, follow it down, concentrate now, and then you come to that axis along the horizontal dotted line, And then if you go down that vertical line, you come to 20 degrees Celsius. Yes? It's working out for us. That's how it works. Increase the temperature to whatever it is to bring down that relative humidity from 100% to 60%. So this is what helps us work things out. And it's very important that we understand this, because when we go into a property and we find we got high levels of relative humidity, but we've got to state what the temperature is, because it could be, well, it's bound to be to some degree, to a great degree, that it's because we've got a low temperature. And what we can do, work out this, and then we can put it into our report to give a more complete picture of the situation. But we do not need to use a psychometric chart when we go into a building. We can use an online calculator, which are free to use, free to download. There are many of them. And so here you can see, if we insert temperature, and if we insert dew point, that will tell us that the relative humidity is too high. So if we want 60% relative humidity, we insert 60% relative humidity, press enter, and it tells us that we need a temperature of 20 degrees Celsius. So it's quite simple and quite straightforward to use. Let's think about thermal bridging. All buildings have a thermal envelope. Any weakness in that thermal envelope is known as a thermal bridge. A typical thermal bridge may be a window, say with a single pane of glass. That is the weakest point. But of course, many buildings these days do not have windows with single panes of glass. We have single glazing, yes, but then again, we may have double glazing, triple glazing, secondary glazing. So it could be that the weakest point is now somewhere else. That somewhere else location could be the window reveal, location A. And why is that the weakest point? Well, if you look at the distance from location A, the window reveal, to the outside face of the wall, the distance isn't that great. If you compare it with location B, the flat plane of the wall internally, and look at that location and its distance from the outside face of the wall, it's much, much greater. So the external temperature is going to have much more influence over what's happening at A compared to B. So the strength of the thermal bridge is the relative difference, I'll say it in these terms, the relative difference between heat loss in different locations. The weakest area of the greatest heat loss is the thermal bridge. But it's the relative difference that determines the strength of that thermal bridge. There are things that could increase the thermal bridge in location A. For example, moisture in the wall itself. Moisture is a conductor of heat. Let's think where that moisture may come from. What about the window frame and its join to the mason's opening? What sort of join is it? Is it just a gap where water and air can go in and out? Is it a seal joint, which is fantastic? Or is it a seal joint that started to break down? And if that's the case, water may get in and it finds it difficult to get out. Increases moisture in that part of the wall, increasing the heat loss, strengthening the thermal bridge. Think of another situation. This is a vapor permeable wall. What if it has a cement render applied to it, which very often cracks? If it does crack, rainwater gets in, finds it difficult to get out. Again, it's increasing the moisture content of that wall in that location, strengthening that thermal bridge. But of course, you also note we've got mould growth. We've got mould growth. And why is that? Well, a lack of ventilation. In an older building like this, originally, there wouldn't have been any draft proofing, so you'd have lots of circulation of air. With a modern window, draft proofed, with trickle vents which are kept closed all the time, and night latches which are never used, you haven't got any ventilation. You haven't got much ventilation in that location. And therefore, that stagnant air achieves persistently high levels of relative humidity, means we got mold growth. So we can think about all the things we need to do in order to deal with this particular problem, which we've just explained. So if you're investigating this problem, you've got to check out the ventilation and the air movement. You've got to look at the joint between the window frame and the mason's opening. You've got to look at the condition of the wall and take action to remedy any problems you find. Of course, some organisations will bring in mechanical ventilation, such as positive input ventilation, to promote that air movement to stop the mould growth from occurring, to deal with that particular issue. But of course, it's not just the owners of the building that need to take action. It's also the occupants as well. To keep those trickle vents open, use the night latches, and regularly check and wipe down around windows where there could be damp surfaces. But the other thing we've got to remember is that this is a traditional building. Why have we got high levels of relative humidity on the surface of the reveals in a traditional building? Because we've applied an impermeable finish. Because if you had the original lime plaster in that location, lime plaster, like many other traditional materials in traditional buildings, is both vapor permeable and hygroscopic, which means it absorbs moisture from the atmosphere when we've got high vapor pressure in the atmosphere, and that moisture is then evaporates outwards and leaves that plaster when we've got lower levels of vapor pressure. So there's almost continuous movement of moisture back and forth rather than stagnant moisture on the surface. So again, in an older building with lime plaster present, the incidence of mould growth in this type of situation should be far less. What we've just looked at is what you can see in A. The window frame is on the outer face and we have a strong thermal bridge. If we look at B, think about it. It's different, isn't it? The window frame is now set back from the external face. So the question for you is this. We will have a thermal bridge in B, but is it going to be weaker than A, stronger than A, or is it going to be just the same as A? Think about it. Work out the logic based on what we've been talking about so far. Think about it. It's going to be weaker because there's a greater distance from the window reveal to the outer face, a weaker thermal bridge. Where we got C, a cavity wall, without any cavity wall insulation, there will be a thermal bridge because that is the weakest point. There's greater thermal conductivity from the window reveal rather than the flat plane of the wall, because we've got the flat plane of the wall, you haven't got solid masonry going straight through, you've got a gap in the middle. And in D we can see that the cavity wall insulation has been installed. And so think about this now. The thermal bridge in D, is it going to be the same as C, weaker than C, or greater than C? And think what gives the strength of a thermal bridge. It is the relative difference of heat loss in different locations. The thermal bridge is alongside the window frame the same as C, in that same location, but will it now be stronger, weaker, or will it be the same? Bearing in mind, part of this wall now, not at the window reveal, but the other part of this wall, the flat plane of the wall, has now been insulated. We'll have a stronger thermal bridge because the relative difference is greater. So, what does this mean for the risks of mould growth? It might not mean an awful lot. It might mean there's good ventilation. But it does mean there's a greater risk of condensation and mould growth on the window reveal. Yes, we need to understand that is a risk that will happen when we install cavity wall insulation. And if you're going into a dwelling and you're going in and you've noticed the window reveal has mould growth on it, you ask the occupant of the building, when did this start? Oh, might say, 5 years ago. You might say, anything else happened 5 years ago? And they might say, oh, well, it was, we had cavity wall insulation installed, and there you have it, because that triggered it. So we need to treat an investigation that sort of way. So what can we do about this? Well, we can insulate the window reveal, can't we? That will sort it out. It may not need much insulation. It may need just an insulated wallpaper or something of that kind. What I'm trying to say is we need to factor in that this is what can happen. And this is part of our investigation. So this is a building I surveyed a few years ago. Again, we take the data on the outside, we take the data on the inside in internal spaces, and the one thing I've highlighted there is absolute humidity. And absolute humidity is not measured in percentage terms, but it's normally measured as the grams of moisture in a metre cube of air. And here we can see, outside, it's around about 7. Inside, it's around about 10. That's a big difference between the outside and the inside. So we've got to analyse these figures. Why is there that difference? Why is it around about 30% greater moisture in the air internally compared to outside? And that leads us into thinking and analysing certain things like, is there too much moisture generation inside this building? Is there a lack of ventilation, or is it both those things? Is the building fabric heavily moisture laden? So we've got to use this data to instigate our investigation into that particular point. And this is a diagram representing a plan of this building. And if you look at it very closely, you look at the annotation starting in sort of the top left-hand corner. Visible damp on floor. Lounge, nearly all skirting boards having moisture content above 20%. High moisture in walls up to 300 millimetres from floor level. High moisture in walls up to about 750 millimetres from floor level, and so on and so forth. What does that tell you straight away? It tells you that the building fabric is heavily moisture laden. Bear in mind, this is not just on a hillside, this is on a mountainside in the highest peak in England and Wales. And buildings which a couple of decades ago would not be suffering the consequences so much from water running off the mountainside, they are suffering a lot today because of climate change. Much heavier rainfall for longer periods of time, meaning there's a lot more water coming off a mountainside running into buildings like these. And as you can see, one of the things we're recommending here is what we recommend in many buildings in this situation, is putting land drainage in to take water away from the building. Water just runs into the walls of this building. The building fabric is heavily moisture laden. Think about some other analysis and using data. If you look at these black boxes, you will see coloured dots. And alongside those coloured dots, we have certain temperatures. That is the surface temperature in those locations if you relate those dots to the diagram itself. The hygrometer, those surface temperatures are ascertained through the surface thermometer from a hygrometer or thermal imaging cameras. The hygrometer is also indicating what the dew point temperature is. And if the dew point temperature is if those temperatures there alongside the coloured dots are at or below the dew point temperature, then we know we have condensation in those locations. But even if the temperatures are just a degree or so above the dew point temperature, then we know straight away then we could have high levels of relative humidity at those surfaces. And with a lack of ventilation, we'll have a risk of mold growth. And we should also understand this. We are just ascertaining the condition of this building at a moment in time during the daytime. So if we determine that these surface temperatures are just a couple of degrees above the dew point temperature, then what about in the winter, in the middle of the night? Because on those occasions, at those times, there's every likelihood that those temperatures will be at or below the dew point temperature, and that is when we get many episodes of condensation. And there lies the limitations of just taking the data at a moment in time. So let's continue by looking at this process. Now we're at stage 8, using electrical moisture meters. And if you look at the top right-hand corner, we're talking about capacitance meters to walls and solid floors calibrated on site. And if high levels of moisture are ascertained, consider using a carbide meter or the gravimetric test for exact moisture percentages in such building fabric. And if we've got cavity walls, we need to use borescopes to inspect the cavity, and all this assisted with thermal imaging. So we need to use the right equipment. And then we have to assess ventilation. Okay, doing everything we're saying in the bottom right-hand corner, but also testing those fans with a vane anemometer. And then we get to the final stage. So at all these stages, from 1 to 9, we are continually analysing the situation until we get to stage 10, where we do our final analysis and we write a report. Hopefully the report will say, we know what the situation is, we know what the problems are, we know what the causes are, and we know what to do to resolve them. Hopefully the report will say that. But sometimes it will not be able to, because we still don't know enough about a building. I can go back to my time in 1981 when I first started environmental monitoring of buildings. I was using the sort of tool or equipment you can see on the left-hand side of the screen. A thermohygrograph, which collects temperature, relative humidity. And you leave it into a property for a week. You go back, you open up the graph paper, you sit down with the occupant of the building, and you look at all those episodes where there was a moisture incident, where moisture was a problem. And you'd find out from the occupant what was going on inside that building at that time. And it could be, for example, every time there's that moisture incident, it was when the bathroom was being used. Yeah. So now we can hone in on the bathroom, that's where the problem is, and investigate it further. These days we can use data loggers, small data loggers. We can have any number of them in a property, and they can do everything plus much more that the thermohygrograph does. And I was working on a project in the late 1980s where these data loggers, late 1990s, these data loggers were being imported from the USA, so they've been around a long time. But the software with them these days is fantastic to analyze the data. And those pieces of equipment can help us analyze a particular problem when we're investigating a building. But of course, as you can see on the right-hand side, the ideal situation is we monitor the building all of the time. And some organizations will do that because they want to nip problems in the bud. They want to determine that they've got poor environmental conditions that could give rise to mould growth issues before the mould starts to grow. And the organisations I deal with, many of them have had their fingers burnt with retrofit that's caused these problems. So monitoring buildings is a way of understanding what is going on all of the time, rather than just one particular moment in time that we usually see when we're conducting an investigation of moisture in a building. So if you look at this overall process, we have a pre-inspection, we do the site inspection, we produce our report, we finalise our proposals, we design and specify the work, we implement the work on site as it worked. We should always conduct a post-completion evaluation, always. Arab's law says you've got to do this, but it makes sense to anyway. As an organisation, for example, as a social housing organisation, you want to know whether the work you've undertaken, the approach you've taken has actually worked. And you may determine at that post-completion evaluation that you've been brilliant. It's fantastic, you resolved it. Fantastic. Don't rest on your laurels. How were you so successful? What did you do so well to end up with a situation whereby you resolved the problem? Find out how you did it, because you want to learn lessons for next time. But also look upon it this way. Can you do even better next time? Can you do some things better? Can you be more effective with your resources and with the time it takes? Always look for continuous improvement. And if you're conducting your post-completion evaluation and you find it hasn't worked, that the problem has come back, why? What did you do wrong? Find out, because you've got to put it right for next time. Learn lessons, learn how you can improve, and then once you've reached a stage where you do this work successfully, always look to see how you can do it better. Because resources are in scarce supply, we've got to see how we can do things better, more effectively, but also more economically as we move forward. We need to continually improve ourselves and continue to improve our expertise. The approach I've been describing to you if you didn't know already, is building pathology. That's this approach I've been describing to you. If we look at the definition from Designing Buildings Wiki, it says that building pathology is a holistic approach to the studying and understanding buildings, and in particular, building defects and associated remedial action. In a medical context, pathology is the study of diseases in order to determine their causes and prescribe treatment. Similarly, building pathology involves the methodical study of buildings, their components and environment to address failures. In my own simple words, building pathology is the investigation and science of the causes and effects of construction problems and defects. It involves inspecting, analysing and monitoring of buildings considering the environment around the building and use. That's what it is. It's about a proper investigation. A proper investigation. And 10 items, if you like, or reasons why it has to be building pathology. 1, it's about understanding the possibility of possible problems in a building. So you've got to really have a good knowledge of buildings, everything about the building, and the possibility of things going wrong. And the hardest problems to solve are the ones that you can't see, but the ones you need to determine exist before the problems do manifest themselves into defects you can see and defects that affect the occupancy of the building. So it's a comprehensive approach. 2, it's about solving problems properly. 3, it's always about finding the cause or causes of problems. And 4, determining solutions that address the cause or causes and understanding that there may be a number of options to address the cause, and we've got to find the right one for our building, our type of building, in our circumstances, in our situation and location. Understanding that the cause may not be the building itself, but it could be its use, it could be the environment around it. But in all honesty, very often it's a bit of everything. But we've got to determine and proportion where does the fault lie. Because if we don't determine that properly, we will not determine what the solution should be. The problem could be due to treatment that the building has received since it was constructed, the alterations, the repairs, maybe the retrofit work that's been undertaken. The problem could be that the building was constructed with defects in the first place due to poor design, poor construction, or poor construction and design. And we know all about that, don't we, when we think of all the high-rise blocks of flats which are poorly designed and poorly constructed. And the problem could be due to poor maintenance, a lack of maintenance, no maintenance, poor repair, inappropriate repair, no repair. And the last point is very important, because when we've determined that these are the ways in which we can do work to resolve our problems, we need to work out if the proposed treatment has any possibility of causing other problems in themselves. So this building pathology thing we're considering, it has to incorporate things I can't describe in detail in this short time scale, but it has to incorporate building forensics, building diagnostics, and to some degree building physics as well. So let's go back to these questions that we asked at the very beginning. What are the most common causes of damp and mould in housing? Well, I would say poor ventilation. Poor ventilation, lack of heating. Why have we got poor ventilation and lack of heating? Well, you can work it out. Sometimes buildings are just poorly equipped with ventilation. Sometimes you also got to look at the way the occupancy is being dealt with as well. A lack of heating, it could be that there's plenty of heating, but it's not being turned on. Building fabric in poor condition, and it's not properly or appropriately maintained. Yeah, absolutely. I see lots of properties in poor condition, ranging from gaps around windows to mortar-filled cavities, which are bridging damp-proof courses and bridge the wall from the inside, on the outside to the inside, leaking gutters which are overflowing, all sorts of problems. I mean, all the obvious ones we can think of, any one of us who do anything to do with buildings. and poorly informed changes, including retrofit. That's a massive one. That's a massive one that we focus on in our 2-day course. And climate change issues. The climate is changing. And there's a whole host of things that can come under that. How can landlords and housing providers identify issues before they escalate? Well, the first point is regular inspections by non-technical personnel. Yeah, anybody going in to advise an occupant in a social housing context about money issues and debt issues, tenant liaison officers, the guy servicing the gas boiler. We've delivered short training courses to those type of personnel to raise their awareness of these issues so they can go in, have a little scout rounds, depending on what their organisation wants them to do to spot any problems, and also to take on board what's being reported to them by occupants. That's the first point. The second point, periodic condition surveys by the technical personnel, for example, building surveyors, who should be taking the approach I've been describing to you today, a building pathological approach that includes building forensics and building diagnostics. And the third point, we need to maintain building fabric and building services so that they always remain in good condition. Fourth point, when it comes to reactive maintenance, we need to be quick. We need to be prompt, because some of those reactive maintenance issues involve water, and we don't want any water being absorbed into the building fabric. We don't want water within spaces increasing vapour in the air within inside buildings, which increases this problem of damp, mould and condensation. The fifth point, technical personnel conducting inspections should be well trained and competent, and I would say, if we want to be sure, they've got to be qualified in that particular subject. And the final point, if we're really serious about this, we should be monitoring environmental conditions remotely, and then we'll know whether problems are brewing up before they actually reveal themselves into defects we can actually see, but also we'll understand how well or otherwise the property is being used and occupied. What are the short and long-term risks to residents if problems are ignored? Well, I could say a lot about this, but I don't want to be scaremongering. But there's a grave risk of physical health dependent on the type of occupant. So we look at moulds, and we're not looking at moulds in detail right now, but some moulds are highly dangerous, especially for very young people, very old people, people who are seriously ill or recovering from a serious illness, or people with immune system disorders, and poor mental health. I can just sum it up as that. And which interventions are most effective in tackling damp and mould at source? Well, the first point is we've got to understand the causes of problem and deal with the causes. Second point, we need to be proactive and undertake preventative actions, taking a building pathological approach and being forensic in our investigation. Remember, building pathology is about understanding the possibility of possible problems existing. So we need to understand all those possibilities and how likely or otherwise they might be. And the third point is we need to install ventilation systems that adequately ventilates the whole building, not just the kitchen and the bathroom, but adequately ventilates the whole building. Systems that contain continuous mechanical extract ventilation, but boosts upon activation by humidistats when we've got high levels of relative humidity. And ventilation systems that cannot be tampered with. And how can contractors and surveyors work more effectively with landlords to reduce the reoccurrence of mould? First point, all personnel need to be trained, qualified and competent. 2, work into robust protocols and tried and tested systems and processes. The third point, we need to have a continuous evaluation on what works and what doesn't work, and have a continuous perspective on learning lessons. The fourth point, we need a robust approach to the initial analysis of the problem. And that's why I showed you those 10 stages of the way in which we do that. And the fifth point, never take shortcuts in the analysis stage and the remediation stage. And finally, always focus on the causes of problems. So in final conclusion, I think you've gathered that we need to know how to do this properly, right from the investigation, right through the implementation. And that means we've got to have competent people. There are 2 training courses that I deliver. There's one they're both available self-paced. But the first one is for people who are just going into buildings, and they may be going in for many different reasons, but not to investigate mould. They're just people who go into the building, and they're the eyes and ears of landlords to have their look. Also, people who work in housing association call centres do that course. But the second course is the only course of its kind that has a specific focus on damp, mould and condensation that achieves an Ofqual government-approved qualification. Now, that's a 2-day course, all delivered self-paced. And when individuals are obtaining a qualification, it means they have come up to that particular standard. And I believe that when it comes to Arab's law and the person who's investigated the problem, they have to sign their name to it. If they got those letters after their name indicating they have a specific qualification in this issue, I think when they're under the spotlight, they may have a little bit more credibility than they would otherwise. But the other thing is, with the second course, that includes live drop-in tutorials with me and free access to a new resource, which is the ESC Hub on damp, mould and condensation. Anyway, if you need any more, you can see the QR code, and thank you very much for your attention. Thank you.